Last lecture today, which is entirely going to be about the CMB. And in particular, what I want to do is to deconstruct this thing, to tell you where all the different pieces come from, and how you can therefore use it, why it is such a powerful probe of cosmology. Okay? So just by way of introduction, that what you saw just now, there is the temperature power spectrum of the cosmic microwave background fluctuations. Okay? And essentially what it is that you have this map of the sky that you take. This was from the Planck collaboration. And what you do is that you look at all the perturbations away from the mean. Okay? So the mean is just the 2.725 Kelvin background that people measured a long time ago. And then you parameterize this temperature fluctuation in terms of this theta parameter, which we've already seen multiple times. Okay, so xi here is the position, ni is the xi is the position on the map, yep. Ni is the direction of the photon, and eta here again is just the conformal time that we've been using. Now, the thing is that so that's the general expression you write down for the temperature fluctuation. But when you make an observation of the CMB sky, you actually project all these fluctuations. What you see is essentially a projection, okay, when you look around, okay? So around 4 pi around you. So, and the projection is essentially that done on the sphere of a surface. Okay, so what you need to do, so this map over here is really a two-dimensional spherical map. So what it means is that it makes sense to analyze this map by decomposing the map in terms of spherical harmonics, okay? And so you have, this decomposition, these coefficients, these are the spherical harmonics, and the coefficients, ALMs here, are essentially the temperature fluctuations. And when you construct the power spectrum of these fluctuations, essentially what you're doing is that you're just taking these ensemble averages, okay? So ALM star, and this CL thing here is the angular CMB power spectrum. Now, so these are the dots that we see over here. This is lifted from the Planck papers. They call it DL, but actually it's just the CLs that I talked about before. And then they also multiply by some factors of L and L plus 1, just to make it kind of as close to a white noise spectrum as possible. Okay, so you render it dimensionless. Okay, so you can compare with a white noise spectrum. And so you have these acoustic peaks. Now, to calculate CL from theory, well, essentially what you have to do is to construct an integral like that. Okay, so K here are your Fourier modes, and then the theta L's here are essentially just the temperature fluctuations that you would expect to see today for a particular K mode, and then you decompose to this spherical harmonics decomposition that I spent quite a bit of time talking about over this past week. Okay, and if you want a precise prediction for this theta L, you need to run CAM or class. That's what these codes are for, to solve that enormous set of equations that I attempted to derive to an extent also in the past week. However, as it turns out, there's actually a neat way to think about the CMB sky so that you get more or less the power spectrum right without actually doing the full calculation. Okay? And so that's what I will do today. So, to begin with, in order to think about a CMB, we should recognize that there is one single event that is basically the most important for the evolution of photon perturbations, and that is photon decoupling. Okay, so this is a very simple cartoon illustrating what's happening. You have essentially, over here on the left-hand side, high temperatures above the decoupling temperature, which I call T star. So star indicates decoupling, okay, today, which is at about 0.25 electron volt. If you want to consider in redshift, that's about a redshift of 1,000 in most models that are close to what we call lambda CDM today. And if you're above this temperature, you have the photons doing a random walk around, scattering of electrons. Okay, and as I mentioned yesterday briefly, when this random walking is happening, you have a tightly coupled fluid between the photons and the baryons that the photons are scattering off, and then you end up getting these acoustic oscillations. Right? Now, then you let your universe cool, and eventually the temperature drops below T star, and then all the electrons that were initially free become bound in hydrogen atoms. So the universe is neutral on the right-hand side, and these photons can then free stream to infinity. And you see these photons as if they're coming from a last scattering surface. So this is the one most important event, photon decoupling, or the last scattering surface. I use these terms kind of interchangeably. So what it means is that if I want to think about a CMB, I can essentially think about it in two steps. Okay? What happens before photon decoupling and what happens after? Okay? In particular, we want to ask what happens to these photons before decoupling on subhorizon scales and superhorizon scales, and then what and so on. Okay? So let's do that. So the I should have taken my notes, so now I have to find them. So let's start with the what happens before. Okay, so if I want to investigate what happens before photon decoupling, and in particular, if I want to focus on those scales that are superhorizon before photon decoupling, and since we're interested in photons, I should focus on those equations to describe the photons. There was one that we wrote down that goes something like this. I'm just trying to find the chalk here. So superhorizon limit, as said, is a limit wherein k is much smaller than curly h. And we had an equation of motion for the photon density perturbations before. So delta gamma dot. And just for definition purposes, the energy density perturbations is the same as 4 times the monopole temperature fluctuation, okay? Scalar. And this thing here, if you go back to what we did yesterday, this is given by an equation like so, okay? It goes like 4 phi dot, where phi is one of the Newtonian gauge potentials. Okay. So if you actually look at the full equation, there's also another term that is proportional to k. But since we're in the superhorizon limit, k is small, so I just set that to 0. All right? Cool. So once I've written this down, it's clear that theta naught, 0 dot is equal to phi dot, which implies immediately that if I look at a solution for this monopole temperature fluctuation as a function of time, I should just have theta naught is equal to phi, the Newtonian potential, plus some constant. Okay? Now, this is general, but remember that we also discussed the adiabatic initial conditions yesterday. And if you had adiabatic initial conditions, then I should expect theta naught of k. And if I take it deep into the superhorizon limit, so I take time back to 0, okay, I should have this thing being equal to minus p phi p, where p stands for primordial, okay, whatever is God-given from inflation, which be a function of k divided by 2. Okay? So if I now use this adiabatic initial conditions and then put it back into my solution over here, then this I can actually also write as phi k eta minus 3/2 phi primordial. Okay, now, photon decoupling is obviously something that happened in the early universe, but as it happened, the photon decoupling actually happens during matter domination. Not very deep in matter domination, it's a little bit after equality, but nonetheless it's still matter domination when photon decoupling happens. And we've seen that during matter domination, the superhorizon solution for phi, okay, so eta star is the time of decoupling. And if we are happily, and since eta star is in the time of matter domination, and we're looking at superhorizon scales, then I can expect phi evaluated at this time to be 9 divided by 10, the primordial value. So again, this is something that we looked at yesterday, a solution that came up with yesterday. Okay, so now if I now use this piece of information again, and then stick it back to the solution for theta naught, what I would find immediately, without, well, I'm not going to do the algebra, you can do that yourself, is equal to minus 2/3 phi. No, sorry, okay, I shouldn't do that. No, actually, I don't stick it there because that's general. I stick it over here, actually. So theta 0 naught k evaluated at the time of decoupling will be equal to phi k star, eta star, and then I have 3/2, and then I should have a phi p over here, but I have also this solution that I figured out during matter domination, so superhorizon. So I can just stick that solution in, and I'll have 10 divided by 9, and then phi k eta star. Okay, and if you just crunch through this, then what you'll end up with is just a simple relation between the photon monopole temperature fluctuation to the Newtonian gauge potential phi k at the same time, at decoupling. Okay? Now, the next thing we're going to do is to form what we call the effective monopole. And I'll tell you in a bit why we do this. The effective monopole is just whatever is the bare monopole over here, and you add to that the other Newtonian gauge potential psi. All right? I said I'll tell you why we do that in a bit. But if you ask what is this quantity on superhorizon scales at the time of decoupling, then I can just take the solution that I found above and then add to this the psi parameter. And since psi and phi are pretty similar anyway during matter domination, what I'll end up with immediately when I do that is that this thing should be equal to 1/3 times psi k at the time of decoupling. And if you then use one of the Einstein's equations to relate the potential, Newtonian potential, back to the density perturbations in the dark matter that we should have at that same time, okay, what I'll find is that I will get minus 6 and then delta C. Okay, where delta C is the energy density perturbation in the cold dark matter. Okay, so that's the effective monopole temperature fluctuation. This is the CDM density perturbation. Okay, note the minus sign. Okay, what does it mean? Well, here's a schematic illustrating what's happening. So it's exactly the same expression written here that I have just derived. Okay? And the key thing here is that the effective monopole is over here, But then this is roughly equal to the minus negative of the CDM density perturbation. Okay? So what it means is that if you see a CMB hotspot, a spot with a high temperature, it actually corresponds to an underdense region in dark matter. Okay? And why is that? Well, first of all, why we calculate the effective monopole as opposed to just using theta naught is as follows. So when you think about an observer who's sitting out here and you're trying to look at the CMB, you don't just see the CMB photon, okay? Because in order for you to see the CMB photon, the first thing that needs to happen is for this CMB photon to climb out of whatever overdense region it might be in. It has to suffer gravitational redshift, okay, on its way to you. Okay? So here, if you look at this green blob here, which might be a photon sitting in a hotspot, so it's intrinsically hot, okay? But when it climbs out, it would redshift, and then it will fall into another potential where blue shift, redshift, and by the time it gets to me, I need to correct for the fact that where I'm sitting does not have the same potential as where the CMB photon had originated from in the first place. So there is a gravitational redshift correction, which goes like 1 plus psi, okay? So that's the reason why it is that when we discuss the CMB monopole, we don't just look at theta naught, we always tag on the gravitational redshift, because that's ultimately what we see. Okay, so that's why we look at this, we construct this quantity. And as I said, it is actually corresponding, if you see a hotspot, it's actually an underdense region. And this result is actually particular to the adiabatic initial conditions that we have implicitly put into the expression. And it just means that the things conspire in such a way that the gravitational redshift would just turn something that looks intrinsically hot into something that looks kind of cold again. Okay? So this is a bit weird, but it's, as said, peculiar to adiabatic initial conditions. If you have different kinds of initial conditions, like a mixture of isocurvature and adiabatic, this hotspot underdense region correspondence does not need to apply. Okay? So it's a bit odd, but this also means that this correspondence here is something that is unique to adiabatic initial conditions, and therefore you can test it. Okay? So that's the first funny thing about the CMB temperature fluctuations. Now, next thing I want to look at is what happens when we go to sub-horizon scales. Now, if we are interested in sub-horizon scales, then clearly, anything that's kind of, these causal effects will have to start to come into play. So by that, I mean the effects of Compton scattering. Okay, so the fact that the photons are scattering off the electrons. And as we've seen earlier, this scattering leads to the photons and the baryons being tightly coupled. Okay, and then you go into essentially what is called a tightly coupled limit if the scattering rate, kappa dot, is much larger than the Hubble expansion rate. Now, yesterday we looked at a simplified form of the acoustic oscillations. We just took the photon equations of motion, which are over here, over there, and then we assumed that the photon velocity and the baryon velocity are exactly the same. Okay, that would be if the fluids are really, really, genuinely very tightly coupled. But in reality, that is not quite so, because you have photons that are ultra-relativistic, and then you also have baryons there which are non-relativistic. But redshifting for relativistic and non-relativistic energy densities differ. So at some point, the the contribution of the inertia of the baryons will become apparent. Okay? And that will actually have an effect on how the acoustic oscillations proceed. Okay, so what it means now is that instead of just dealing with the photons and then assuming that the velocity of the photons and the velocity of the baryons are the same, I'm now going to also account for a slight difference between the velocities. And we're going to do that by also incorporating the baryon equations of motion, which are written over here. Okay, so density perturbations, velocity perturbations, again you see this coupling. I've introduced a parameter r, okay, and 1 on r is defined essentially as just 4 divided by 3, and then the background photon density divided by the background baryon density. This quantity here scales like 8 to the minus 1, okay, so it's time dependent. This thing is called a baryon to photon ratio, not surprisingly. And what it leads to essentially is what is called baryon loading. Okay. So let's do that. Let's see what we can do with that. Okay, so we're looking at subhorizon, right? And ultimately what we want to do is to turn the photon equations of motion over here into a second order differential equation. But the first thing I need to do is to somehow get rid of this pesky VB over here, which belongs to the baryons. I also want to turn that, I want to find an expression for VB, which is essentially related to V gamma, okay, plus some additional parameters. And the way I do that is to take the equation of motion for baryons, okay, we take the velocity equation for the baryons, and then rewrite it in a smart way. So I write VB naught is equal to V gamma naught, and then R divided by kappa dot, and then V dot B naught minus K psi plus H V B naught. Okay, this is exactly that second equation for baryons. I've just turned it around, rearranged it, right? Now, one more step I can do is to introduce some factors of H here and there. So I have V gamma naught minus R. I'm going to insert an H over here, divided by kappa dot, H being the Hubble parameter, and then I have a 1 on H, V dot B, minus K on H, psi plus VB naught. Okay, still exact. Now, the next thing we are going to do is to recognize that if I'm in the tightly coupled limit, what I'm doing essentially is just assuming that VB is equal to V gamma naught plus some order H divided by kappa corrections, right? That's what it is when I do tightly coupled limit. So what this means is that what I can do now is to make use of this rewritten form of the velocity for equation for the baryons, and then kind of systematically expand it out to leading order. Well, leading order is this, but also a correction to order H on kappa dot. Okay? So we'll do that. VB naught is roughly equal to V gamma naught plus R H on kappa dot, and then so the first term here on this side we have 1 on H V dot B, right? So what I'm going to do is to replace this with V dot gamma instead. okay? Because that's the leading order expectation for how V dot B should be anyway. Okay, so I've done that. And there are higher order terms as well, obviously, but I'm going to drop those. Okay? And then I have K on H, psi, that's the same as before. And then last but not least, we have another V B naught over here, which I am again going to replace with just V gamma, and then drop the rest. Okay? And then I will have higher order terms that are second order in H divided by kappa dot. Okay? So that's good. Now what I have is an equation, and it's an expression for VB naught, which is entirely in terms of quantities, perturbations for the photons. I have a V gamma over here, V gamma, and that's good because now what I can do is to plug this expression here back into the equation of motion for photons. Okay? So VB is over here, but now I've got this thing, which is written in terms entirely of photon quantities. I plug it back in here, then I have two equations that are entirely in terms of just perturbations in the photon fluid and nothing else. Right? And then the next steps are really just as usual, as we've done many times before. You construct a second order differential equation out of these two first order differential equations. And what you end up getting, once you do that, is an equation that looks something like this. Delta gamma plus R dot 1 plus R, delta gamma dot plus K square on 3, 1 plus R, delta gamma on the right-hand side. And then on the left-hand side, you also have the potentials, which are 4 pi double dot plus 4, and then R dot 1 plus R phi dot minus 4 divided by 3, K square psi. Okay? So just to recap again, I got this thing out of combining these two equations together using the expression for VB. Okay. Okay, now here is the equation again, actually, but written in terms of the temperature fluctuation. Okay, so again, delta gamma is 4 theta naught. Same equation over there, just a bit neater maybe, because we don't have to carry around all those factors of 4 all over the place. Let's look at it. So what do we have? We have, well, essentially the structure of a harmonic oscillator again. On the left-hand side. It's actually a damped harmonic oscillator, because you have a damping term over here, which wouldn't be there if the baryon to photon ratio is exactly 0. Okay, so that's what we had yesterday. We didn't have this term when we did not include the baryons. Again, on the right-hand side, you have the source terms, so the Newtonian potentials. So this is essentially an equation of motion for a damped and driven harmonic oscillator. Now, if I look at this term over here, you have the k square and then a sound speed again, Cs. But the sound speed is a little bit different this time. Okay, the sound speed this time is not just, the sound speed square is not just 1/3, which is what we had yesterday, which would have been the case if you have like an exactly ultra-relativistic fluid. But now we are looking at photons coupled to baryons, and the baryons are non-relativistic. And the way the baryons are manifesting themselves is basically through this R parameter. Okay, so in other words, if R is large, then the sound speed would be lower. Okay, and this is called baryon loading. Okay? So by coupling photons to baryons, you lower the sound speed of the combined fluid, which is not surprising. And by the way, R is tiny. If you want a numerical value for that, it's actually very much less than 1. That is because, well, the omega B is 5%. As we know, omega gamma, which is the photon energy density today, that's like 10 to the minus 5. Okay, and and A over here is, well, also a small number because we're looking at a fairly high redshift. Okay, so even though the baryon loading is causing the sound speed the sound speed to go down, it's not like it's dragging it down to 0 or anything like that, because you never really have so much baryons in your mix. Okay. There's one more thing we can do with the, I mean, okay, you know it's a harmonic oscillator that gives you acoustic oscillations. But there's actually one more game we can play, and that is we can try to find an approximate solution to this equation. So as said earlier, decoupling happens during matter domination. Okay, and during matter domination, we also saw a solution from yesterday that the potentials phi and psi should be more or less constant. Okay, so I'm going to assume that here as well. Furthermore, I'm going to go into the limit where the oscillations term, k square c square, is much larger than the damping term. All right, you can rewrite this actually in terms of the sound speed that I gave over there. So this would just be k square 3 1 plus r, okay, and this has to be larger than this bunch of stuff. I have r dot there, that's the time derivative of my r parameter, but r goes like a anyway, so you can already see in your head that any kind of time derivative of r would basically be proportional to the Hubble parameter, okay, because it's just a dot. So as it turns out, the right hand side is actually exactly the same as just r divided by 1 on r squared, and then the Hubble parameter. So again, you can see that this, what you're doing essentially is to compare the wave number and the Hubble expansion rate, okay, plus with some r factors in between, which that r is less than 1 anyway. So this condition is very easy to satisfy if you're sub-horizon, because when you're sub-horizon, k is in any case larger than h. Okay, so this is quite easy to satisfy. So, what that means then is that once I apply these approximations, my equation of motion will simplify significantly. In fact, it simplifies to theta naught 0 plus k square cs square theta naught is equal to minus k square 3 psi. So it's just a harmonic oscillator with a source term. I can solve that with the WKB solution. Okay, so it has to be WKB as opposed to just any solution, because the sound speed is dependent on time. But nonetheless, the WKB solution is easy, because it would just be, well, again, we write it for the effective monopole, because that's what we see anyway. It's a function of k and then time, and then we generally expect this solution to look like this. And we'll have oscillatory terms, some constant multiplied by sine, k rs. I'll tell you what rs is in a bit. And another constant, and it'll be a cosine solution as well, KRS. And then there's also a particular solution that comes about because I have a driven oscillator. Okay. So that's the monopole solution. I can, in fact, also derive a similar kind of solution for the dipole temperature fluctuation, which I won't do, I'll just give you the answer. The dipole looks like this. It'll be theta 1 naught. Again, it's a function of k and time, and is actually related to the monopole solution. It's actually just as a derivative of it. So you see the sound speed coming in here, C1, same C1 cosine KRS plus CS, and then constant 2, C2, sine KRS. That's the dipole solution. Okay, so they're out of phase with each other. Now, at this point, as I said, I've defined this quantity RS. Well, actually, I haven't defined it yet. I've used it. I haven't defined it yet. And now I'm going to define it. RS is just defined as essentially the sound speed, which is a function of time. And then you integrate over time from 0 to the present time. Not the present time, sorry, the time that you're interested in, eta. Does anyone know what this is? It is the sound horizon. Okay. Actually, it's the co-moving sound horizon if we want to be very pedantic about it. And this co-moving sound horizon is the single one most important parameter in CMB physics. It tells you how far sound can travel from the beginning of time up to the last scattering surface. And then we see it pop up quite naturally in our acoustic oscillation solutions. Okay, it goes in here, RS. Now, one more thing. I still haven't determined the coefficients, C1 and C2, but you can more or less guess what they need to be, because we saw earlier, just like 10 minutes ago, that there are superhorizon fluctuations for the effective monopole, right? Theta naught plus psi. This immediately tells us that the mode that is excited cannot be the sine mode, because the sine mode starts from 0. The cosine mode, on the other hand, starts from 1. Okay? So the fact that we have superhorizon fluctuations means that the only solution here that makes sense is for C1 to be 0, but C2 to be finite, and then matched to the superhorizon solution that we derived earlier. Okay. Okay. So let me just write it down. So the superhorizon K mode solution we saw earlier was theta naught, 0 plus psi, and then K eta, that was 1/3 times psi, right, for adiabatic initial conditions. Okay, so if I take this solution over here and let time go to 0, I should have a solution that matches this one, okay? And that automatically implies, as said, that C1, the sine mode, is not excited, but you will have the cosine mode, and if you do the matching, you'll find that the cosine mode has a coefficient that evaluates to theta naught, 0 plus 1 plus r psi, and you evaluate that if you take eta to 0. Okay, so finally, this tells us that the two solutions we should see are the following. I should have for the monopole theta naught plus psi k eta is equal to theta naught plus 1 plus r psi, okay, evaluated k equals 0, eta equals 0, the cosine of that, and then krs minus r phi. That's for the monopole, and for the dipole, we have the other one. We have theta 1 k eta is equal to the sound speed, and then again the same coefficient, but you excite here the sine mode instead. Okay. So again, the fact that we pick out the cosine mode for the monopole came from the superhorizon solution, and the superhorizon solution itself came from assuming the adiabatic initial conditions. Okay? So there's a chain of assumptions. Adiabatic initial conditions, and you match to that, and you end up exciting only the cosine mode. If you had a mixture of adiabatic and also curvature modes, then in general, you can excite both the sine mode and the cosine mode. Okay? And that actually leads to quite a difference in how the acoustic oscillations present themselves when you finally look at a CMB sky. And of course, since we know that we don't really see adiabatic, I mean, we still really see isocurvature modes, everything looks adiabatic, it's the cosine mode that we work with here anyway. All right, so these are the acoustic oscillations, and all of that, basically, this calculation here is just to justify the cosine mode and also to introduce the co-moving sound horizon, which is very important. But let's now just go back to look at physically what's happening when we have acoustic oscillations. So this here is the acoustic oscillations as a function of time. For a very simplified system, I think I have actually neglected, yes, I've neglected the baryons here for now. So R has been set explicitly to 0, and I'm assuming that phi and psi are constant. And I've picked a particular Fourier K mode and then look at how the thing evolves with time. So you see these acoustic oscillations. So this here is an overdense region, the monopole temperature fluctuation in an overdense region. So if you look at the schematic over here, we're basically looking at a photon that is sitting at the bottom of a potential well. So what's happening here to the photon fluid when you're at the bottom of the potential well is that gravity would want to pull you in, pull the photons in. And the pulling would compress the photon fluid. But at the same time, the photons themselves have this intrinsic pressure, and they like to escape. Okay, and that corresponds to these blue arrows over here, which are basically pressure trying to push the photons out. Okay, sometimes pressure is successful and you push very, very successful versus gravity, and so instead of compression, you have rarefaction of the gas, and so you have compression over here, and then rarefaction over here, and then compression, and so on and so forth. The cycle keeps going. Okay, it's just competition between gravity and pressure. A similar thing is also happening in the underdense region, so that will be this photon that is sitting up here. When gravity starts to pull down, then momentarily the energy density of the photons up here is thin, so you end up have a drop, a dip here in your theta naught. But then pressure will push these photons out of the potential well and then contribute to thickening the gas up there again. So you end up with a peak, like the theta naught oscillating up again. Okay, so again you have this competition, both in the inside, in an overdense region, as well as in an underdense region. Okay. That's just the theta naught by itself. You can also plot the effective monopole, which I have done here, theta naught plus the psi. That's the red line, okay, that's the effective monopole. So it's oscillating around 0. And I've also plotted the dipole alongside, which, as we've seen here, is exactly out of phase. Okay, so it's cosine for the monopole, sine for the dipole. Okay. Now, that's evolution as a function of time. But what we're really interested in is to have a look at a snapshot of the perturbations at the time of photon decoupling. So I can also plot my solutions in an alternative way. So here what I'm doing is basically plotting what is called what I call a spectrum. Okay, so I've just taken my monopole solution and my dipole solution and then just square them. Okay, because that's basically the power, if you like, okay, in these modes. And instead of plotting this as a function of time, I'm plotting this as a function of k, the wave number. So I fix the time and I just look at a snapshot of the different modes and see what they're doing. But still, you know, I should get an oscillatory solution, and that's what I'm seeing, right? And red is the effective monopole, and dipole here is in blue. Now, one thing you can already establish using what we have written down here from the WKB approximation, a solution, is the positions of the peaks. Okay, and in fact, the first peak on the monopole occurs here. And there's a very simple expression you can write down. The location of the peak is just n times pi divided by rs, the sound horizon. Okay, and n can be, well, okay, if you want the first peak, you get n equals 1. You want the second peak, you put in n equals 2, so on and so forth. You have a series of acoustic peaks. Okay? And essentially the position of the first peak that you see here corresponds to the K mode that has completed exactly one compression at the time of photon decoupling. Okay, so you compress and then rarefact and then compress again. So first peak is exactly one set of compression. Right, so these are the peaks on the last scattering surface. Now still I'm assuming R is equal to 0. I haven't loaded the system with baryons yet. The next thing I'm going to do is to load the system with baryons. Okay, then what's going to happen is, well, you still get acoustic oscillations, but this is the R equals 0 case that we saw before, and once I put in baryons, what I see is that my oscillations are a little bit different. There's a slight change to the speed at which the oscillations are happening, as we saw before, because oscillations affects the, baryon loading affects the sound speed. But there's another thing that is actually even more obvious of baryon loading is the fact that the changing R here changes the amplitude of the oscillations because of this one on R that occurs here. Okay, so you go from -1, both go from -1, but this one here kind of overshoots and goes above 1 compared with this case. Okay, that happens in the monopole as well as the dipole. Maybe it's not so obvious, but just take it from here. It does happen. Okay. So overall, what it means is that if I look at these oscillations here, particularly the red monopole, effective monopole oscillations, is that you're offsetting the midpoint of the acoustic oscillations. Okay, because everything is, instead of being oscillating around 0, you're actually oscillating a little bit above as a result. Okay, that's interesting. Well, actually, physically, why that is so is actually quite straightforward to understand. And essentially, it's because by loading your photon baryon fluid with a lot of inertia coming from the baryons, you are basically allowing allowing the fluid to want to sit down here in the overdense region. Yeah, because there's just so much more inertia pulling down, and as opposed to pressure pushing up. Okay, so your overdense regions basically becomes even more compressed as a result of the baryon loading. Similarly here, if you're in an underdense region, then this photon baryon fluid that's sitting up there wants to move down, and you don't have quite so much pressure to push it back up. So again, you have basically more compression than you have the rarefaction. Okay. So if I now ask again what's going to happen if I look at a spectrum of the monopole perturbations and the dipole perturbations at the time of photon decoupling, then I go from this initially nice and evenly sized peaks across the spectrum to this situation where I have a lower peak and then this first peak here being kind of pushed up, and then a lower peak again, and then up and down and up and down. Okay, so I have now uneven heights for the odd and the even peaks. Okay, and the height ratio between the odd and even peaks depends on exactly how much baryons you load the photon fluid with. Depends on R. Okay, So this case here, as said, has been, these pictures here I have plotted, assuming phi and psi are constant, but the essential features of these uneven, odd and even peaks due to barrier unloading will remain even if you account for time dependence. Okay, so that's what happens up to the CMB photons, up to the last scattering surface, up to the time of photon decoupling. Keep that in mind. Keep this picture here in mind. For now, store it, and we'll come back to it later. Now, next thing is to consider what's going to happen to these photons after decoupling. Okay. Well, as you can probably guess, what happens after decoupling is essentially just free streaming, right? And if you recall from maybe yesterday or the day before, we wrote down a Boltzmann equation for these CMB temperature fluctuations, which looks something like this. You have a d theta d eta plus ni d theta like that. Ni is the direction of the photon, and then we'll have a bunch of gravitational source terms over here, and then a bunch of collision terms on the left-hand side. Okay, and this second term here is basically what is responsible for free streaming. Now, if I was doing this in Fourier space, then these equations just become d theta naught, d eta, I, k, and I theta naught plus da da da, and then collision. Okay. K is the wave vector again in some direction, and Ni is the direction of the photon, as we have said before. So if I'm to solve this, it's immediately clear what kind of solution I should get from free streaming. I should have theta naught, which is generally a function of K, eta, and the direction of the photon, will be roughly schematically given by some initial condition, okay, which I'm going to pretend is the initial conditions at the time of the last scattering surface. And the free streaming will be represented just by a simple plane wave solution. Okay. So I will have exponential minus I ki ni, okay? And then the time today minus the time at the time of photon decoupling. That's a free streaming solution. Schematically, anyway. Now, this is just the temperature fluctuation, like so, in terms of the photon direction and the wave vector. But in CMB physics, we always like to decompose things, right? And we, in the case of looking at CMB temperature fluctuations, we decompose with spherical harmonics. And since we are looking at m equals 0, the scalar modes at the moment, the spherical m equals 0 spherical harmonics are essentially just Legendre polynomials. Okay, so in other words, we usually do a decomposition like this: theta naught, and then ki, eta, and I, and then you sum all the way from L equals 0 to infinity, and then you have some prefactors like that, and then you have the theta L, k, eta, and then you have the Legendre polynomials. Okay, or the m equals 0 spherical harmonics, if you like. And this is actually what we want. So what it means is that if I want to find a free streaming solution for these multiples, theta L. What I need to do is actually go back and decompose this thing as well. Okay. Then, if you do that, that's actually quite straightforward what you should expect to see. I will have theta L, k eta. I'll still have the dependence on the initial conditions. Okay, that will be theta 0 evaluated on the last scattering surface. And what the decomposition does to the plane wave there, essentially, is to turn it into a set of spherical Bessel functions. JL, K, eta minus eta star. Okay, and that comes about because when there's a plane wave expansion that you can do, exponential I k dot x is basically just L equals 0, theta, some prefactors, and then JL, kx, Legendre, k dot x. Right? So you turn this plane wave over here into a set of spherical Bessel functions. So that's generally what we expect to see in the expect to see what free streaming does to the perturbations on the last scattering surface. So you have the monopole and dipole solutions over here, and then you tack onto that the set of spherical Bessel functions that would bring these perturbations from the monopole to the dipole and spread it all to the higher multiples. Okay. So that's the effect of free streaming. And that was a schematic discussion of what free streaming does. You can actually do it properly. And what you find if you actually did it properly is you'll find the monopole gets spread in practically, well, what I've written up here. The dipole free streaming is a little bit more complicated, but you still don't deviate from the fact that you have some spherical Bessel functions that are basically transporting all the power in the monopole to the higher multiples L. Okay, so that's the effect of free streaming and how it spreads the monopole power and the dipole power to higher multiples. Now, a couple more things we can do with this to try to understand what's happening. So here is a set of spherical Bessel functions for actually j equals 0, 1, 2, and 3. And they are oscillatory. And what you also see here is that they peak. Okay, so L equals 0 is a bit hard to see, but if you look at L equals 1, it's the green line over here, and it peaks at about 1. Okay, so it peaks at x looks like L. The blue line here is for L equals 2. It peaks a little bit later, consistent with this trend where it peaks where the x in the argument is equal to the degree of that spherical Bessel function. A bit hard to see for these low multiples, but in CMB physics you need to go out to L of 1,000. Okay, and if you go out to L of 1,000, this relation actually holds pretty well. So the fact that the spherical Bessel function peaks at x goes roughly equal to L means that if you look at a particular multiple moment, theta L, then it gets its most contribution for those k modes that satisfy this condition. Okay, x roughly equal to L. And if you use the x that is actually in here, then what you find is that those k modes that are contributing the most to a particular multiple moment is basically those ones that goes like k roughly equal to L divided by the conformal time difference between today, when we observe the thing, to the last scattering surface. There's another way to write this time difference. Since we're dealing with photons that travel at the speed of light, this time difference here is essentially the same as the co-moving distance to the last scattering surface. Okay, so we have L divided by chi star being the co-moving distance to the last scattering surface. Right, now, so again, we can go back and use this information and then ask ourselves where should we expect to find the acoustic peaks. Well, so we saw earlier that there are a series of peaks from the acoustic oscillations, right? and they peak at a value k peak, which is essentially something related to the sound horizon. So what I can do now is to use this information about where we expect what k modes should contribute most to which L modes to basically give us a rough estimate of where the peak CMB peak locations should be. So we go like n times pi, the co-moving distance to the last scattering surface divided by the co-moving sound horizon at the time of photon decoupling. Okay, so this is another important relation in CMB physics because we can look at the temperature power spectrum, look at where your acoustic peaks are, find the locations, find your L, and then essentially go backwards using this expression to figure out what the co-moving sound horizon was, okay, as well as how far away the last scattering surface is. Now, as it turns out, that was free streaming, okay? As it turns out, free streaming is not the only thing that can happen to the CMB photons after decoupling. There is another thing which is actually very important, and that is called the ISW effect. ISW stands for I is integrated, SW is Sexworth effect. And it turns out that if you have time-dependent potentials, then there's an additional term that you need to write down that would also contribute to the multiple moments that we see today. Okay, so you have these time-dependent things over here, phi dot, psi dot, and you're going to do this line-of-sight integral from 0 to the present time. This term here is called the ISW effect. Now, why do I have a ISW effect term? Well, it's quite straightforward. So before we go to ISW, let's look first at the Sexworth effect. So actually, we already sort of talked about it before. Remember that if you have a photon that is coming to us and is initially in an overdense region, the first thing that needs to happen is that this photon has to climb out of the potential well, in which case it will suffer redshift. And it will blue shift and redshift and blue shift and redshift, and by the time it gets to us, the temperature that we actually observe is the intrinsic temperature fluctuation plus a correction due to the gravitational redshift suffered by this photon, right? So that's Sexworth. Integrated Sexworth is something that happens when the potentials are changing in time. So then you can again see the schematic that try to illustrate the situation. So you have at first your potential wells looking like that and your photons trying to do some climbing out. But it climbs out, but all at the same time your potentials are decaying away. Okay? So by the time it crosses this barrier and then falls back into the next potential well, the amount of blue shifting that the photon will suffer will be actually a little less than the amount of red shifting it suffered when it was trying to climb out in the first place. Okay? So therefore, you have to, in order to account for how much net red shifting or blue shifting that your photon should have, you need to do this integral to sum over basically the entire history of how the potential has evolved. Okay, so that's the ISW effect. Right. Now, there are actually two ISW effects that people talk about in the literature. One is called the early ISW effect, and the other one is called the late ISW effect. And that is because ISW effect depends on the potentials evolving, right? And during matter domination, the potentials are practically constant. So for the late universe, the only time where you would expect to see the ISW effect kicking in at all would be around the transition from radiation domination to matter domination. Okay? There's still a little bit of residual radiation left over at the time of CMB decoupling, which you can still see. Okay, that's called the early ISW effect. Okay? So which are effects due to transition from radiation to matter domination. And the effect of this is most prominent if you're looking at the first peak of the CMB fluctuations, the temperature power spectrum. The late ISW effect is related to the transition from matter domination to dark energy domination. Okay? And this is a very recent thing, and the contribution of this late ISW effect to the CMB temperature power spectrum is mainly primarily to the left of the first peak, in fact, at the very low multiples. Okay, so we have all the ingredients. We have what the spectrum on the last scattering surface. We free stream that, and then there's also the ISW effect that we have to tag on as well. And now what we can do is to put it all back together. So that's what we have. So this here, the polar line is just the monopole solution, which has been naively mapped by just using this relation between K and the location, K and L. Okay, so that's the solar line. And if I had properly done the free streaming by multiplying with the what do you call those things, spherical Bessel functions, then the actual signature is a little bit shifted. Okay, so you free stream them properly, you get the dashed line. Now, the next thing we can do is to add the dipole. The dipole adds in this way. They add incoherently because of the orthogonality relations amongst the spherical Bessel functions. They add incoherently, sorry. And so what adding the dipole does essentially is that you raise everything by a little bit. Okay, so I mean, just going back to the previous plot over here, your oscillations here can be 0, but free streaming already removes the power from 0. And adding the dipole removes it further away from 0 again. And last but not least, we have to add the ISW effect, which is around the first peak if you're looking at the early ISW effect, and there will also be some late ISW effect here and the low multiples, which are not shown in this picture as the last term. And so that's it, really. If you compare that with the real power spectrum, it's pretty much quite right, for the first 3 peaks anyway. Okay, so that's height in first peak from the ISW effect, and then these regular acoustic peaks that you see for second peak, third peak, and then so on and so forth. Actually, right now we have measurements of 7 acoustic peaks, by the way. Now, this is not actually the complete picture yet. There's one thing that I did not discuss, and that's called diffusion damping. And diffusion damping is what is responsible for actually removing power at these very high values of L. And that comes about because, so far this whole discussion is about how photons tightly couple to electrons, right? But, and how the photon fluid and the electron fluid are moving as one. Okay? In reality, this is never ever exactly true. And that is because what is really happening is that your photons are doing a kind of random walk between scattering. Okay? And random walk immediately leads to the effect of diffusion. Okay? Your photons are going here, there, and so on and so forth, and then eventually they end up over there. That's the phenomenon of diffusion. And what diffusion does is that it washes out those temperature differences on scales smaller than the diffusion length. Okay? So my photons move from here, diffuse from here to there. All the power in the temperature fluctuations are removed on this diffusion length scale. The diffusion length scale you can estimate. It's basically just what's called lambda d, and you take the square root of the number of scattering centers, and you multiply that by the mean free path of the photon, and if you plug in all the quantities that are relevant for cosmology, effectively this lambda d is just 1 divided by the square root of the number of free electrons that we have. The Thomson scattering cross-section again enters because it's Compton scattering that is responsible for this diffusion. And h here is the Hubble rate. And if you plug in numbers, then it turns out that the diffusion length is of order a few megaparsec at the time of photon decoupling. And that's what leads to the decrease in power in the CMB power spectrum once you go to, say, L of 500 or so. You have these nice acoustic peaks, and then suddenly, boom, everything drops off because of diffusion damping. In fact, if you go up to about L of 2000, what you start seeing is the red line here being the prediction, theoretical prediction, becoming below what we actually observe in the data. Okay, this basically signifies that the diffusion damping is removing so much power from the CMB on these scales that over here you're basically completely dominated by the foreground. Okay, you're dominated by the foreground by so much that there's just no point doing measurements anymore here in these extremely high multiples. Okay, so that's sometimes this bit here is called a damping tail for obvious reasons. It's diffusion damping tail, and they have been measured for a while now. It was only first measured maybe about 15 years ago, ACT, SPT, and Planck, of course, can also measure this now. And now, so a lot of the experiments are kind of focusing on this end, just to make it more accurate. Okay, cool. So that's diffusion damping. Anyone would like to ask anything before I very briefly talk about how you can use all of the stuff I talked about to constrain parameters? No. No. Okay, doesn't matter. So as said, lastly, very briefly, I want to say where all these cosmological parameter constraints come from. I'm sure you've all seen pictures like these ones. You know, you have these nice posterior around omega B, dark matter, etc. Where do they actually come from? Well, let's first of all define what we want to constrain. Okay, we want to constrain the matter density, including dark matter. Okay, and matter density is omega m. Baryon density is another thing what is typically constrained by the CMB, that's omega b. There are parameters describing Hubble expansion rate, spatial curvature, dark energy, etc., and they usually come in the form h omega k and omega lambda. And of course, there are also some inflationary parameters that are typically part of the standard game. There are other parameters that are being constrained as well by the collaborations, things like number of neutrino families and effective neutrino mass sum, okay, another popular parameter to use. The key thing to understand, of course, is that when you look at the CMB temperature anisotropies, or even polarization anisotropies, they don't actually measure these parameters at all. Yeah, what you're measuring when you do your experiment are temperature fluctuations. You don't measure these cosmological parameters. So next time you write a paper and say Planck has measured the matter density, please don't. Okay, it doesn't. It infers it. Okay. But as we have seen in the last hour or so, these parameters enter into various quantities of interest. Okay, these parameters enter into the sound horizon, into the co-moving distance to the last scattering surface. So, and because the way the CMB looks depends on these these key quantities like co-moving sound horizon and the co-moving distance to the last scattering surface, you can you can turn it around and use the CMB to constrain those things, and hence also these parameters as well. So, to begin with, the easiest thing to constrain is the baryon density. And that is because, as we saw earlier, if you have baryon loading into the CMB, you will end up causing uneven heights in the odd and the even peaks. Okay? Just coming from this R parameter, which is itself dependent on omega b. So that's basically where we get constraints on the baryon density from the CMB from. You're just really looking at how changing R would end up affecting these odd-even peak height ratios. Okay, and here's a picture of an actual CMB power spectrum computed for certain fixed parameters and also for varying omega b. So the green line over here, the blue line over there, and the light blue line, they all have different values of the baryon density. And what you see here in particular, if you look at the comparison between the first peak and the second peak, you see that that if you have a small baryon density, that's the dark blue line, you have smaller variations between the first peak and the second peak, compared with the green line, which has a larger variation because that's a larger baryon density. And for the largest baryon density, 0.044, that's the light blue line that has the largest variation in the first to second peak ratio. Okay? And this signature is very hard to mimic by anything else, which is why you never hear about the omega b tension, because this is just really well determined. It's very hard to mimic with anything else. okay, by anything else. So that's the easiest. There's another thing that is also quite nice, easy to determine, and that is the early ISW effect. As I said earlier, the ISW effect has to do with changing potentials, okay, and you only see that during matter domination, transition from radiation domination to matter domination, which basically makes its appearance around here, around the first peak. You also have a late ISW effect, which is at a much lower multiple. Now, you can determine the size of the ISW effect by essentially just comparing what the first peak looks like to another odd peak. Okay? You don't compare with an even peak, because the even peak is influenced by R, right? You compare with another odd peak further down, okay? So first to third, let's say, or the fifth, or whatever. Okay? You can, now the thing is that since the ISW effect is related to the transition from radiation domination to matter domination, you can expect it to be sensitive to exactly when equality happens. Okay? So in other words, what the ISW effect, early ISW effect, allows you to establish is essentially the redshift of matter radiation equality. Okay? So this is another parameter that is extremely well measured in lambda CDM. It's better than 1%. And just from looking at early ISW effect. Now, here's an expression here relating the set equality to the matter density, okay, and also the radiation energy density. Now, the radiation energy density in standard lambda CDM is just photons plus 3 families of massless neutrinos. Okay, so in other words, if you can establish that equality from the ISW effect, and since we know what the photon energy density is, and we can also calculate the energy density in massless neutrinos, then in fact what you have done is to pin down this omega m h squared parameter, the matter density. Okay, if you know set equality, you know the matter density, assuming you know the radiation density. Okay, so that's what it's saying here. If N effective is known, if you know how many neutrinos you have, then the ISW effect gives you essentially a measurement of the matter density. Now, of course, if you didn't know what N effective is, if you're actually interested to probe N effective, then it's inconclusive at this stage. Okay? Okay, so here's an actual picture illustrating the effects of the early ISW effect. So again, 3 cases with different matter density parameters. So the green line is, okay, I should have done this a bit better to have some order. So the blue line is the one with the smallest matter density, and followed by the green line, followed by the light blue line. And again, you can see that in all 3 cases, the third peak are kind of similar, okay, because that's when your early ISW kind of just dies down. The early ISW really just makes a contribution here, okay, and you can see relative, okay, the third peak are the same, and then you have, very different first peaks. Okay, so you use that, as said before, to pin down the redshift of equality. If you stare at this for long enough, you also notice that there's a little bit of an uptilt of the power over here. That is actually from the late ISW effect. Okay? And that is because when I plot these 3 curves, I have different matter densities, right? If I have different matter densities, then I'm also changing the way I transition from matter domination to dark energy domination at a much later time. So this does 2 things actually, changing the matter density. It changes the early ISW effect. It also changes the late ISW effect, okay, later on. Now, so that's that. Now, as I mentioned earlier as well, there's the angular sound horizon is another thing we can pin down, okay? So essentially, the angular horizon, sound horizon is just basically about where the peaks are, okay, where they occur in L space, okay, and as we wrote down this expression earlier, L peak goes like pi times the co-moving distance to the last scattering surface divided by the co-moving sound horizon, Rs. Now, when we derived this thing here, we had assumed the spatial curvature to be exactly 0. But if I had allowed for spatial curvature, then actually the co-moving distance needs to be replaced by the sign of the co-moving distance if I have a positively curved universe, or the hyperbolic sign if I had a negatively curved universe. Okay? So overall, if I want to write down this expression in a more general way, I can write the following. I can define a thing called theta s, that's called the angular horizon in literature, and it's just pi divided by the location of the first acoustic peak, okay, location in L or the first acoustic peak. And if I use this stuff over there, and also, replacing the chi with a sign, what I'll find is that this is equal to the scale factor at the time of decoupling times the sound horizon at the time of decoupling as well, so the same sound horizon that appears here, divided by the angular diameter distance to the last scattering surface. Okay? So that's another famous quantity that we use. Now, if we examine the parameter dependence of the sound horizon, okay, by just plugging in what expectation for what these dA and things should look like. After several lines of algebra, what you arrive at is a dependence, parameter dependence that looks something like this. We expect this thing to depend on omega m. It will also depend on any kind of spatial curvature that we have in the universe. It will depend on the Hubble expansion rate. And so these are the 3 parameters, 1, 2, 3. Now, some of these we can already measure by other means. Okay, so for example, as I said earlier, you can use the early ISW effect to probe set equality. And if you make assumptions about what kind of radiation you have in the universe, then this set equality measurement is essentially the same as saying that you have measured omega m h squared. Okay, so if that is the case, then the only parameters that are remaining and unconstrained is the omega k parameter and also the Hubble expansion rate. And these are degenerate. Now, if I didn't know what the radiation content is, if I didn't know n effective, then again, the story is inconclusive because I don't have a measurement of omega m. And in fact, I end up having a more complicated 3-way degeneracy, and there's still some more work to do, but I can say more about that later. But let's just stick with the first case where n effective is known, and you have a measurement of omega m and h squared. Then, well, I said omega k and h are degenerate as far as the angular sound horizon is concerned. And to see that, let's have a look at an actual prediction again. So green here is the case for a flat universe, and the dark blue is for a negatively curved universe. It looks like this, and they are no, actually, no, it's positively curved because it's a minus sign of definition. And the other line is the light blue line, which is for a omega k that is positive, so that's a negatively curved universe. Okay, so you can see here the location of the acoustic peaks are completely shifted. Okay, that is because, as I said, you are basically looking at a sound horizon, and you divide it through by the angular diameter distance, which itself depends on curvature. Okay, so this tells you that changing the spatial geometry changes the way the acoustic peaks are basically projected onto L space, and then you shift all the positions. I said earlier that omega k is degenerate with the Hubble parameter, so let's also look at how changing the Hubble parameter can actually change the signature as well. So again, I have 3 cases. H of 0.7, H of 0.4, and H of 1. And again, you're seeing the shifting of the acoustic peaks due to these different values of H. So that's what I meant when I said that H and omega k are degenerate as far as the location of the acoustic peaks are concerned. But that is not to say that the CMB data cannot tell the difference between the effect of spatial curvature and the effect of H. And that is because we still have the late ISW effect over here. Okay? Now, we call that late ISW effect is coming from the transition from matter domination to dark energy domination. So I'm going to stuff around with H, the Hubble parameter. I'm also going to end up changing omega m. Okay, so here I fix omega m h squared, right? But if I'm changing changing h itself, then my actual omega m would also be varied across these three cases. If I change the matter density, then I'm changing the way I transition from matter domination to dark energy domination. And that manifests itself in the late ISW effect. So that's why you see these dramatic differences between these three cases when I vary h, which we did not see before for variation of omega k. Okay? Because omega k has nothing to do with ISW. So in the end, even though I can't tell the difference between varying h and varying omega k from the acoustic peaks, I can still tell the difference between these cases by looking at ISW at late times, and so I can measure them anyway, okay, with the CMB alone. So we have practically pinned down all the parameters, I think, okay? But there's still one thing that has become very important in the last 15 years, and that is the measurement of this damping tail, okay, by various probes like ACT, SPT, etc. Okay, and primarily what they are probing over here is the angular damping scale. Okay, so we saw earlier that there's this damping due to diffusion, and there's a damping scale that we can calculate, which is related to the how photons do random walk and diffuse through the electron fluid. That thing there, that quantity, is also highly cosmology dependent. Okay, so we can make use of figuring out exactly where the damping begins to try to get to that diffusion scale. Okay, so that's what we do. Now, the angular damping scale is just similarly defined to the sound, angular sound horizon. So you take the damping diffusion scale that I sort of briefly showed earlier, and you divide that through by the angular diameter distance to the last scattering surface. And again, you can ask what is the parameter dependence of this theta d. And again, what you find is, well, it depends on omega h, mh, it depends on omega m h squared, omega k, h, etc. So it's a similar set of parameters, but in a slightly different way compared with the parameter dependence of the angular sound horizon. And in fact, if I look at theta d and ask how it relates to theta s, as it turns out, theta d is really just omega m h squared times theta s. Okay? So this is actually very powerful because it tells you that if I manage to figure out the angular damping scale from the data and I have a measurement of the acoustic scale as well, then the ratio of these things will provide me with an independent measurement of omega m h squared. Okay? And this is true whether or not you know your dark and know your radiation content. Okay, remember that with early if you use early ISW to get to omega h squared, you have to make an assumption about the radiation content. Okay, here you don't. You get these two ratios, out pops the omega m h squared altogether, and it's completely independent of what you assume for spatial curvature, dark energy, etc. That's great because if I can get an independent measurement of omega m by just looking at the ratio of theta d and theta s, then I can also figure out what is the radiation content by going back and looking at the ISW effect. And that's the reason why it is that people talk so much about using the damping tail to measure the so-called ineffective parameter. Okay, any kind of excess radiation that you have in the universe due to light relics or, I don't know, thermal axions, light sterile neutrinos, etc. Anything that can increase your ineffective to beyond 3. So it's an irreducible signature of ineffective. It's all showing up in the damping tail. Okay? And I think that's it. I'm not that badly over time. So I will shut up now, and thanks for your attention. No, I did not even talk about massive neutrinos at all in the last week. It actually makes. Let's see if I have a picture over here. Okay, so you can see in the CMB, the main signature is going back to the power spectrum, right? So this is K, this is P of K, and power spectrum looks like this, right? If I put some massive neutrinos in, what happens is that you will have more or less the same power spectrum over here, but then at some point, it will drop off a little bit. Okay, and where it starts to get suppressed depends on the neutrino mass, okay, the individual neutrino masses, and then this gap over here, this suppression, delta P on P, is essentially going like the energy density in the neutrinos divided by the energy density in the matter. So when we do neutrino mass measurement, we are really looking for a suppression in the power spectrum. Okay, just like the final suppression over here and maybe some of these effects. So it's kind of a little bit like the discussion for baryons, except that in the case of baryons, you are always, what determines where the suppression begins is when the baryons are released from the photons. In the case of neutrino free streaming, where the suppression begins depends on what kind of neutrino mass you have. So you could have a heavier neutrino mass doing this, and a lighter neutrino mass might have a signature like that. Okay, so you start a little bit earlier, but you get a little bit less suppression. Yeah. So I did not even talk about that. No, it's an extra layer of complication. Yeah.